This is Mr. Halsey of 8 Squared Sufficiently Understood Science, and today we're going to be taking a look at the electromagnetic spectrum. So the electromagnetic spectrum is a complete range of different wavelengths that compose electromagnetic radiation. And this ranges from things like radio waves, microwaves, to the visible light that we see, as well as more powerful waves such as ultraviolet, X-ray, or gamma rays. Now, these are only really differentiated by their wavelengths, and that's going to increase their power or decrease it. One thing to keep in mind, though, is that all of these waves that we're going to be talking about do travel at the speed of light. So they are moving around the universe really, really fast. So electromagnetic waves are formed when an electric field, which is shown in our red arrows, pairs with a magnetic field shown in the blue arrows. And one thing you'll notice is that whenever there is an electromagnetic field or wave, you have the same size electromagnetic wave, electric wave and magnetic wave. This is because they are pairs. They're not alternating, they're pairs. And we'll take a little bit closer look into these waves in just a minute. But typically what we'll see is the magnetic field off in this direction and the electric field like that, and they're all going in the same direction. So this is a pairing of electric field and magnet field. Now, a lot of people get confused when we're talking about electromagnetic waves because one of the lowest ends is going to be radio waves. So people very often confuse them with sound waves. So what's the difference between sound waves and electromagnetic waves? To explore this, I'm going to do a little bit of fair use here and show you guys a clip of a movie. So have you ever watched a movie and you are greeted to an exciting scene like this? Pretty cool, right? So what would that sound like for real if we were observing this in space ourselves? Let's take a look. Not that exciting. So the question is, though, why can we see the action but not hear it? And it's not because I'm being cheap and decided not to use any audio or anything like that. It's because sound waves and electromagnetic waves are quite different from one another. Electromagnetic waves are unlike sound waves because they don't need molecules or a medium to travel through. These sound waves are known as mechanical waves. They need a medium, whereas light waves, like the reflection and of those objects so we can see them, do not require a medium. This means the electromagnetic waves can travel through air and solid materials, but they can also travel through empty space. So they don't need anything to make them move. Whereas sound waves, the reason we sound the way we do is because our voices are vibrating the air. So that old phrase, in space, no one can hear you scream, is absolutely true. So this is why astronauts on spacewalks use radios to communicate. They can't yell out to one another, but they can use electromagnetic waves, such as radio waves. So radio waves are a type of electromagnetic wave, and so they use those to communicate back and forth. And since those signals are being sent at the speed of light, there's basically no delay. And so they get their message across very quickly. Very efficient for space travel. Radio waves, television waves, and microwaves are all types of electromagnetic waves. They only differ from each other in their wavelength. And wavelength is the distance between one wave crest to the next. So if we were looking at a transverse wave, which is what this is, this chart right here, right here at the very top, where I've marked that X, is the top of a crest. And so we'd measure the distance from the top of the crest to the other crest to get the wavelength. So the crest is the top, and at the bottom, we have the trough, which is the bottom here. You can measure from trough to trough as well to get the wavelength. So waves in the electromagnetic spectrum are going to vary in size, from extremely long radio waves the size of buildings to very short gamma rays smaller than the size of a nucleus of an atom. And so we're going to take a look at some of these different waves, but we need a couple more terms before we can. So to understand waves, we need to know wavelength and frequency. And we kind of have an idea that wavelength means it is the distance from one peak of the wave, known as a crest, to the next one, so crest to crest. But what about frequency? So frequency of a wave is the number of waves per second. An easy way to understand this is looking at a radio dial. If you are an 88.7 FM, that means you are receiving 88.7 waves per second. And as you go up to, let's say, 106.5 FM, you've increased the number of waves per second that you are receiving. And so radio stations broadcast at certain frequencies. And so frequency is just the number of waves per second. So the higher the frequency goes, the shorter the wavelength, such as with gamma rays. This also means you'll get a lot more higher energy. You'll get more energy. Lower the frequency, like radio waves, you get a very long wavelength and low energy. So the longest waves to shortest waves goes radio waves, microwaves, infrared, visible light, which is what we are able to see, and that's all, ultraviolet, X-rays, and gamma rays. So let's take a look at these. So radio waves have a much longer wavelength than the light waves that we see. The longest waves can be several kilometers in length. So let's define a kilometer for those that don't know. A kilometer is 1,000 meters. And we're talking about several of these. Whereas the shortest ones are only millimeters. Okay? And so that is much, much smaller. Those are the little tiny lines on your metric ruler. So some uses for radio waves are, of course, radio broadcast, amateur radio, television, mobile phones, so everything you use in your house, your Wi-Fi works off radio waves, your Bluetooth headphones work off radio waves. Most of our communication technology works off radio waves. One thing to keep in mind is, once again, a lot of people get confused with radio waves and sound waves. They are not the same thing. Radio waves send information. Okay? So the radio in your car is taking that information that the radio waves are sending, decodes it, and turns it into music. And so it's just taking information and creating the music based on the information. And we just don't really see it happen. That's why a lot of modern car stereos also will send the name of the song as well, and maybe the station information. And so that's all sent on the same wavelength. Now, speaking of radio stations, different parts of the radio spectrum have been allocated to the various services. This is mostly done by the FCC, which is a governmental agency here in the United States, the Federal Communications Commission. And so what they'll say is, okay, so radio, so if we have, there's our wave here. Radio stations, you can operate between here and here. TV stations, you guys can operate between there and there. Cell phones, here and here. And so they basically break it up and say, okay, you can use this frequency. Maybe they only want that much frequency for Wi-Fi. And so they can decide how those radio waves are going to be used so they don't interfere with one another. Now as we move on, let's talk about microwaves, the next strongest wave. And they have a very short wavelength that are actually easily absorbed by water. And this is why we use them in microwave ovens. So when it comes to your microwaves, what happens is when the water in your TV dinner absorbs the microwaves, the energy of the microwave is converted to heat. And basically it boils the water off on the inside of the food, causing it to cook. This is why microwave food doesn't really taste the same as like grilled food. Sometimes you get really close. Sometimes you get good stuff. But microwave food tends not to taste the same because it's actually using the water of the meat or the plant that you're cooking to cook it. And so it makes the water molecules vibrate faster, and this cooks your food. Now, a fun little experiment you can do at home, and I'm going to start with this. Do not turn on the microwave when you do this. Do not turn on microwave. Okay? Disclaimer. So anyway, the question is, why don't those microwaves just seep out of your microwave oven? Well, if you look closely at the glass, you'll notice that there are a lot of little holes. Not like open holes, but it's a little metal mesh. That is a Faraday cage. It prevents the rays, the microwaves, from actually escaping because the holes are smaller than the microwaves, and so the microwaves can't get out. Whereas, you can still see in. And so since radio waves, which run your cell phone, are bigger than microwaves, they won't be able to enter. And so what you do is you put your phone in the microwave. Do not turn it on. Once again, please do not ever turn it on with a cell phone in there. You'll ruin probably your microwave and definitely ruin your cell phone. But what you do is you put it in there, you close the door, and you have a friend try to call your cell phone, or a parent try to call your cell phone. And because the waves can't go in, your cell phone will not be able to pick up signal. It's basically blocked from the outside world. Once again, do not turn on the microwave if you try this experiment at home. So now moving on to infrared. You're probably most familiar with these in your television remote. So these radio/light waves have a very short wavelength. Their wavelength is a little longer than the visible light spectrum, so we cannot see it, but it can be detected by special infrared film or even by animals and military technology like night vision goggles and things like that. Animals like the pit viper, though, have adapted to be able to use infrared. They have infrared detectors so they can find their prey in the dark, making it a lot easier for them to hunt. Now we get to what we can see. All this stuff we've talked about, we can't see any of it. And so, as far as visible light goes, I'm going to erase this one because it looks just so terrible. Okay, we only see that small little fraction. That's all we see. Now, one thing we have to keep in mind, red, orange, yellow, green, blue, indigo, and violet are the colors of the visible spectrum, or Roy G. Biv. You've probably heard that before. One thing we need to keep in mind and kind of rework in our mind is when we think of hot, we think of red. And when we think of cold, we think of blue. But when it comes to the visible light spectrum, as far as energy and heat, red is actually the cooler end, and blue and purple are the hot end. And so it's counterintuitive to what we typically think, but it's just something we're going to have to work past. So this also explains things like laser pointers. Most laser pointers that you are able to purchase are in this red area of the spectrum, lower energy. You can sometimes get green ones. They're typically a little more expensive, but they are available commercially. They are a lot more dangerous though. They can hurt your eyes much faster. Lasers that are blue or purple are typically not available for civilian use, but they are out there. So the further we go along from red to purple, the more powerful these waves are going to get. And this is basically the extent of what we can see. So past that, oh, by the way, really quick, the red lasers are what we'd use for like DVDs, okay, and CDs. And we call them Blu-rays because they use a blue laser, which has more energy, allowing them to read data a lot more pinpoint accuracy and get a lot more out of it. So these waves, these ultraviolet rays, ultraviolet, have very high energy and very short wavelengths. These are shorter than visible light, and some animals like honeybees can actually see ultraviolet light. You can blame ultraviolet light for a lot of stuff in your life, especially things like sunburns. So if you get sunburned really easy, UV light's the culprit. So some plants have white flowers, and at least you think that they're all white, but they may appear to be different colors to a honeybee because of the amount of ultraviolet light which they reflect. The reason why your shirt may be red is because it's reflecting ultraviolet light, or it's reflecting red light. So if we have a shirt here, once again, I am a terrible drawer, but that's okay. So I have a shirt here that has been dyed red. Okay, this shirt has been dyed red. And so we walk out into the sun. We have red light hitting it, orange, yellow, green, blue. And I don't have really much of an indigo, but we'll go with that. And kind of a purplish violet. So this shirt's being hit by all these different colors, but it's going to absorb this and reflect that. So when your eye sees it, it's going to see red. And so whenever it comes to these flowers here, we may only see a white flower on a white background. And that doesn't really work out for plants. Plants want to stand out with their flowers to attract pollinators. And so we may not be able to see it, but this is probably what a honeybee sees. Stands out a whole lot more. So it's reflecting ultraviolet light. We can't see it, but it is reflecting that ultraviolet light. So X-rays have so much energy and such a short wavelength that they go right through you. However, they can't get through bone as easily as they can get through muscle tissue and other things. And so we use this in the medical field to basically look at your bones, to get a picture of what you're like on the inside. And the reason it doesn't work is because your bones contain so much calcium. So we use X-rays a lot in the medical field. The shortest wavelength are gamma rays. Up here at 10 to the negative 12, about the size of an atomic nuclei. These are fairly nasty ones. They have very high energy and can even go through metal. X-rays get stopped with metals. So gamma rays and X-rays, they can cause cancer because they're so powerful. However, they are being used to also destroy cancer cells. This is called radiotherapy. So these cancer cells, basically what they do is they bombard them with gamma rays and X-rays and kill off the bad cells in hopes that good cells will come back. So to me, it's quite inspiring to think that we take this gamma ray, which if our atmosphere was hit with a gamma ray burst from a supernova star, we completely burn off our atmosphere. And we take this very destructive force in the universe and we take it and we shape it to help people who really need it. I think that's really awesome. So here is our EM spectrum right here, the increasing energy and the increasing frequency as we come through, and the decreasing of the wavelength. This is a really good diagram, and you can see different uses for those wavelengths. So we're going to stop it there for today. I hope you enjoyed the tutorial. Make sure to like, share, and subscribe, and hit the bell notification to know when we upload a new tutorial. This has been Mr. Holsey with A Squared Sufficiently Understood Science. Join us next time as we start to go over some more of these components of the universe.